Now we're going to do problems that I call overhill and underhill. So these are problems where you imagine a ball or a mass on a track, and you want to know how fast does it need to go to stay on the track. So this is underhill. This is the ball's on a loop track. How fast does it need to go? So you have this intuition that if it goes really fast, it easily stays on the loop, like that. And if it goes slower, it's kind of maybe it'll stay on, oh, barely. And if it's too slow, it'll fall off the track. So the question is, how fast does it need to go? So let's see what we get. So how slow, in the case of underhill, how slow can you go and stay on? So let's draw it real quick. It was a loop track. We'll pretend it was a perfect circle like that. And you've got a mass approaching the loop at some velocity. Of course, it's going to slow down and then speed back up. What you really care about is how fast does it need to be going when it's at the top. So we'll say this is the velocity we want, actually. Okay. How fast does it need to be going to stay on, or how slow can it go? We say how slow can it go because when it's going really fast, it'll definitely stay on. And as you slow down more and more, eventually it'll fall off. So it's really the lowest speed that you can go. So to get it, you use everything we've been learning about in this, this unit. You draw a free body diagram and you say, let's see, there's mg down, pulling it down. And what other forces are there? Well, the track pushes on it. There's a normal force. We don't just think about a normal force when something is sitting on a table. We also think about a normal force when things are moving. So there's also a force down I could draw like that and call it N. So free body diagram, forces, and now we apply the laws of physics. And we say the sum of the forces is ma, Newton's second law. We're just going to do it in this direction, down, because that's where all the forces are. Right? So really we're doing it sort of in the radial direction or the centripetal direction, whichever one you want to think about, because we're really, at this point, we're talking about circular motion. It's not really circular motion going up and down because the acceleration is at some weird direction relative to the velocity, but at this moment, all the forces and accelerations are this way, the velocity is this way. So at this moment, it is in uniform circular motion. So let's look. We're going to define also, just for this problem, we're going to say positive, or downward is positive, right? So down is the positive direction. So let's add up our forces. We have mg down, positive. We have N, the normal force, is pushing down, so it's positive. And then we have m, the mass, and then the acceleration, in this case, at this moment, when it is in uniform circular motion at v, is v squared over r. It's just the centripetal acceleration. V squared over, and I'm going to call it big R because it's a constant radius of the track, and v squared over r. Let's see, you might say, oh, but I thought the acceleration had to be down. The acceleration is down, remember? So v squared over r, even though v is this way, it's in a centripetal acceleration. It does have an acceleration down like that, AC. Go ahead and call it AC. Okay. All right, so then we look at these terms, and this is where we can kind of try to intuit what's going on. We got this term because it's circular motion. That is just the acceleration you need, and we know it points down towards the center of the circle. This term, though, is constant, mg. This force doesn't change. Right? So if we want to go at variable speeds and have different mv squared over r, different centripetal acceleration time of the mass, we're going to have different forces. And mg can't change, so it must be that the normal force changes. And we know that it does. If you go slowly around the track barely had to push you around. If you go faster on the track has to push really hard, right? So what you want to think about is that the normal force is variable, but this is the big part. It only points down. A normal force can't pull you back up. It can't suck, right? A normal force only pushes in the direction normal to the surface. So it's not, this normal force has to change to make it all work, but it's not continuously variable to any value. It can be 0, and it can go to a higher value. So one way to solve these is just kind of intuitively say, well, the limiting speed then must be when this is 0, so I solve for v. And that is correct. That's how you do the problem. But let's look at it and see if we can do that a little more mathematically, just if that makes you feel better. Let's solve for the normal force as a function of the speed. So what normal force are you going to get for any speed that you go? And you turn this around, and this comes over here. Oh no, this goes over there, and you pull out the m, and you get that the normal force is m times v squared over r minus g. So that's fine. That means that the faster it goes, the bigger normal force you need. That's fine. But then you remember, no, the normal force can only point down. We've defined down as positive. The normal force can never be negative. You say, but n is always greater than or equal to 0. Right? Well, if this is always greater than or equal to 0, then this must always be greater than or equal to 0. All right, and you cancel the m because it's 0 on that side, and you say, oh, v squared over r must be greater than or equal to g. You say, okay, then this velocity, this critical slowest velocity you've got, is that v must always be greater than or equal to the square root of gr. And this is mathematically the answer. V must be greater than or equal to that. How slow can you go and stay on? Would be the equal. You can get down to the square root of g times r. If you go faster than that, you'll be fine. If you go slower, you basically have too much gravity pulling you down. The normal force is all the way to 0. So if you want to accelerate slower than that, you got too much force, and that's why you fall. So that is underhill. Next we'll do overhill. I call this one When Will It Slide? And the subtitle is A Way to Measure μs, the coefficient of static friction. So when will it slide is done by its a standard mass on an inclined plane problem. So here's your incline at theta, and you put a block on it. And you just ask what's going to happen to the block. We could think of this in a Cartesian system like this, plus y direction, plus x direction. But a lot of times these inclined plane problems are easier if you rotate your coordinate system and talk about a coordinate system where you have a direction sort of parallel to the surface, along the surface, and a direction perpendicular to the surface. So I'm just going to identify those with these two symbols, with the parallel symbol and the perpendicular symbol. And we just got to decide which one we want to use. So right now, when will it slide basically means we're thinking about when will it begin to accelerate down the surface, which means we want to think about what is the acceleration in the parallel direction. So we probably want to work in parallel and perpendicular sort of coordinate system here, rather than x and y. All right. So let's see. Let's draw a free body diagram of the block. It's kind of at an angle like that. And let's see, what do we have here? We've got mg down. Always have mg down. The normal force is pushing back, but it's always normal to the surface. So normal force isn't up, it's in the perpendicular direction. So you got a normal force from the plane pushing up. And you've also got a friction force. There's a static friction that's applied to this. It always resists motion. The forces tend to want to pull it this way, so the friction force is that way. Right, so you could draw your free body diagram like that. And you can see some of them are in x, y, and some of them are naturally in parallel and perpendicular. Okay, so we're going to go with these two. So we write now Newton's second law. Everything we do is by Newton's second law. And let's first do it for the perpendicular direction. The sum of the forces in the perpendicular direction is the mass times the acceleration in the perpendicular direction. We're not writing vectors because these are vector components in one of the two directions. Okay, so we're defining up as positive in the perpendicular direction, so the normal force is up in the perpendicular direction, so N. And then the friction force has no component perpendicular. It's all along the surface, so we just need the component of mg in the perpendicular direction. So I can draw it over here and say, oh, there's a component this way, and there's a component that way. And if I draw it like that, we got to think, oh, where's theta? Theta is here. Because if I let this go really small, yeah, that's theta. it takes me a while sometimes. So we have mg here, and sine, so cosine is that component, mg cosine theta. And it's in, which we call negative, so minus mg cosine theta equals 0. It's not moving in the perpendicular plane, right? It's sliding along. It's balanced forces, so equals 0. This is, in fact, how you find the normal force when you're not just sitting on a flat surface. You know, when everything's level, the normal force just equals mg. But when you're tilted, it gets smaller. So in this case, the normal force just equals mg cosine theta. So that's what we learned from the perpendicular. But we care more right now about the parallel. Right? So the sum of the forces in the parallel direction equals the mass times the acceleration in the parallel direction. All right, so we defined this as positive parallel. We actually ended up putting the friction force positive. It doesn't matter. F. And the negative one is gravity pulling it down, because gravity has a component this way, and down this must be the sine. Sine is opposite over hypotenuse, so mg sine theta, down the thing, negative minus mg sine theta. So that's the forces that way. And we're asking, when does this become greater than 0? What's it going to take for that to become greater than 0? That's when we have a problem. Right? All right. So now, the friction force. What is it? It's always mu times the normal force. So the static friction coefficient, mu s, times n. And then the rest we know, minus mg sine theta must be, or what happens when that becomes greater than 0, and we get an acceleration. Well, the normal force we got over here. Right? So it's not always just mg straight down. We're on an incline, so the normal force is reduced. So we plug this into here, and we get mu s mg cosine theta minus mg sine theta must be greater than or equal to 0. Or when does that become greater than 0? And since we got a 0 on the right, we can pull out the common terms and then just cancel them, because we have 0 over here, just as though it were an equal sign. We could make it greater than or equal if that makes you feel better. So we get rid of the m, we can get rid of the g, and we're left with mu s cosine theta must be greater than sine theta. Mu s cosine theta must be greater than or equal to sine theta. That's right when it will happen. As soon as we cross, we become greater than that. There's a nicer way to write that, is to bring the sine on the other side. Sine over cosine's tangent, right? So as long as the tangent of theta is less than or equal to mu s, it won't slide, right? This is the point where it will begin to slide. So we're saying that we got to keep tangent theta below mu s, and that's the critical point. So what that means is we have a very easy way to measure mu s. All you got to do is get an inclined plane, get a block. In this case, it's just a weight. And I will lift this, and we'll watch theta get bigger and bigger. So let's see, about right there. So what is that? About 30 degrees. Right, so the coefficient of friction between this and this is the tangent of about 30 degrees. Let's do it again. We should get the same thing every time, right? If the friction's the same every time, right about there. Let's do it again. Right about there. Every time, because the friction's the same every time. So that's the easiest way to measure mu s. I'm sure we could think of harder ways. In this problem, we're going to figure out the acceleration of something where we have a pulley like that, and one side is hanging a mass m, and from the other side is hanging a mass 4m. Setups like this are called an Atwood machine. So this was used to study early studies of kinematics and measurements of the acceleration due to gravity, and we have a very cool Atwood machine. So here is our department's Atwood machine, very old, probably about as old as the building, but I can't really use it as a demo, unfortunately, for two reasons. One is it doesn't work, so I don't know, I could probably fix it if I had, 6 months to spare. And two is I can't actually get it out of the door anymore. So the building has settled around the Atwood machine, and we can't even bring it into the lecture hall. So we're just going to have to do the Atwood machine theoretically. We'll do the theoretical version without the demonstration. So the critical points you want to remember here are that tension is constant throughout the setup. Throughout. Remember, a pulley, if we're thinking of it as massless and frictionless, then it will perfectly transmit the tension. So we have the same tension here that we have here. So to figure out how this accelerates, we really just apply Newton's laws to each one of these. We do a free body diagram on this mass and one on this mass, and we just see what we get. So let's see, but let's think about coordinates as well. It's always good. This one we can do in Cartesian coordinates if we want, because everything is basically just moving up and down. It's really a one-dimensional system. So let's see, let's do M. So if we think just the free body diagram on M, well, the weight pulling it down is mg. And it's being pulled up by tension T. We don't know what it is yet. So we could write the sum of the forces and the y equals mass times the acceleration on the y. If you're ever just completely lost on how to do a problem, just write Newton's second law. It's probably the first step. So the forces in the y, we have tension T up because the string doesn't have tension, but it applies a tension force to an object. And so here it's up. And then minus mg down, and that equals the mass ma. Right? So we can't solve for tension because we don't know the tension and we don't know the acceleration. Right? This is not a static problem where this side is 0. We're actually going to have this thing, it's clearly going to accelerate if you have any intuition for this sort of thing. Let's see, let's do the 4m, the larger mass. Let's see, free body diagram, it also has tension T pulling up. It has 4mg pulling down, larger force pulling down. Okay. So some of the forces in the y equals the mass times the acceleration in the y. So in this case, tension pulls up minus 4 mg down equals 4m. So here and here, it's the general mass from Newton's second law, and I'm plugging in the actual mass. So that's why I switched that to that. Here, the general mass from Newton's second law, and I'm plugging in 4m. Sorry, that got a little ambiguous. And it's the same A, except it's negative, right? It's in the negative direction. So we know we're going to assume that this will accelerate down while this accelerates up. We're assuming a few things as we go in here. And if we do that, if we assume they're opposite directions because of the action of the pulley, then we can use the same A. Right? It's the same magnitude we're putting in the direction. Okay. So what do we have? We have 2 equations and 2 unknowns. Right? The unknowns are the tension and the acceleration. The equations are right there, one for each mass. So the quickest way to solve this one, it looks like I just equated the tensions because we were asked for the acceleration. Right? So we could say mg plus ma. This tension equals 4mg minus 4ma. Right, and that all looks correct. So now we just solve for acceleration. All the m's go away. And let's see, we're solving for acceleration. So why don't we bring these 4a's over here and have 5a and bring this g over here equals 3g. So we see, the acceleration is 3/5 g. All right, and that is even correct. So it accelerates at 3/5 the acceleration of gravity. That's another thing an Atwood machine can do for you, is it can let you study acceleration and like slow it down. You don't have to have 9.8 meters per second squared. You get 2 masses similar to each other, and you get much slower accelerations for more precise measurements. We could also get T. The tension is the same in each side of the cable. And if A is 3/5 g, it'd be easiest to get it from here, right? Ma plus mg. So it's 3/5 g plus 5/5 g, it's 8/5 g. Oh, mg. All right. So the tension is somewhere between the weight of this one and the weight of that one.